Hello students, today we will discuss duality in linear programming. So let's start.
So today we will discuss duality in linear programming. The given original program is called primal program. This program can be rewritten by transposing or reversing the rows and the column of the algebraic statement of the problem. Inverting the program in this way result in a dual program. The variables of the dual program are known as dual variables or shadow price of a various resources of a given problem. The duality in linear programming has some useful aspect. Number one, if the primal problem contains a large number of constraints, that is the rows, or a small number of variables, that is the column, the computational procedure can be considerably reduced by converting it into dual, then solving it. Number two, it gives additional information as to how the optimum solution changes as the result of change in coefficient and the formulation of the problem. Number three, duality in a linear program has certain far-reaching consequences of economic nature. This can help manager to compare the alternative course of action and their relative values. Calculation of the dual check the accuracy of the primal solution. Economic interpretation of the dual helps the management in the making of future decisions. Duality is used to solve linear program problem in which initial solution is infeasible. So let's try to understand what is duality. So before going to that, to understand the dual, let's try and get an upper estimate of an objective function of a following problem without solving. So we are considering what's one problem. This is a maximization problem. Z is equal to 10x1 plus 9x2 subjected to 3x1 plus 3x2 less than equal to 21, 4x1 plus 3x2 less than equal to 24, x1 x2 greater than equal to 0. So Z is your objective function, this is subjected to. So constraint 1, constraint 2. So let's do one operation here. Multiplied constraint 1, that is 3x1 plus 3x2 by 10. If you do that, you will get 30x1 plus 30x2 less than equal to 21. So as you know, 30x1 plus 30x2 is greater than equal to the objective function 10x1 9x2. So we can consider 210 as a upper estimate. Similarly, if the constraint 1 is multiplied by 4, then we will get 12x1 plus 12x2 less than equal to 84. Here also 12x1 plus 12x2 is greater than equal to the objective function 10x1 9x2. So we can say that 84 is the better upper estimate of this problem. Now similarly we consider the constraint 2, this one, into 3. If you do that, then it will become 12x1 plus 9x1 is less than equal to 72. And if you observe here, 12x1 plus 9x1 is greater than equal to the objective function 10x1 9x2. So we can say that 72 is the better upper estimate of the given problem. So similarly, if you consider both the constraint 1, suppose 1 is multiplied by 3 plus constraint 2 multiplied by 1. If you do that, we will get 9x1 plus 9x2 plus 4x1 plus 3x2 less than equal to 87. So if you compare all the constraint, upper limit by considering the multiplication, you will get 2, 10, 84, 72, 87. So out of these 4, 72 is the better answer. So we consider that. The purpose of using upper estimate is to understand the duality of the linear programming. So this is your original problem, z is equal to, which is a maximization problem, 10x1 plus 9x2 subjected to 3x1 plus 3x2 less than equal to 21, 4x1 plus 3x2 less than equal to 24. Now if we multiply, suppose the constraint 1, first constraint by A and second constraint by B, where A and B both are greater than equal to 0, such that 3A plus 4B greater than equal to 10 and 3A plus 3B greater than equal to 9. Then 21A plus 24B is the upper estimate of Z, this one. So this is a generalized representation of what we did a few moments ago. Now we want to minimize this upper estimate and we will get another linear programming. Now we can write the same thing in a linear programming methodology. This is minimization, minimized, this is suppose W 21A 24B subject to 3A 4B greater than equal to 10, 3A 3B greater than equal to 9, where AB is greater than equal to 0. So let's try to understand this. So here we are considering the upper estimate. So here A and B, this combination A and coefficient A and B cannot be greater than equal to 10. Combination of these two. Again, this A and B for this one is cannot be greater than equal to 9. And ultimately our intention is to find out the upper estimate, which is equal to 21A plus 24B. Now if you replace this particular equation, full equation, replace AB with x1 and x2, we will get minimize 21y1 24y2, this is suppose W, subject to 3y1 4y2 greater than equal to 10, 3y1 3y2 greater than equal to 9, where y1 y2 greater than equal to 0. Right? Similarly, if you write the original equation, which is maximize z equal to 10 x1 9 x2 subject to 3x1 3x2 less than equal to 21, 4x1 plus 3x2 less than equal to 24, x1 x2 greater than equal to 0. So if you compare these two inequalities, you will get this portion, this original, the original problem is called primal, and this new linear programming, which is derived from the primal, basically is called dual. The meaning is that by using dual, we can check whether this primal is result in the primal is equal or not. So it is very essential. So here, how to convert a primal into dual, that is important. So let's try to compare this example to understand the things. So in the primal and the dual, the maximization problem in the primal is converted into minimization problem, and it is a vice versa. And number of variables, the number of variables in the primal is basically number of constraint in the dual, and number of constraint in the primal is basically number of variables in the dual. Right hand side constant of the constraint, right hand side constant of the constraint is objective function coefficient for the dual. So this is your right hand side constant 21 24 21 24. Similarly, objective function coefficient is 10 and 9, right hand is for the primal, right hand side constant of the constraint. So this is the right hand side constant of the constraint, and it is a matrix of the coefficient for the subjective matrix. This one, look at here, 3 3 4 0 3 3 4 0. This is for primal, and for the dual is the transpose of that, that is 3 4 3 3 3 4 3 3. So in that way we will convert the primal into dual. Hope you understand the basic concept about it. In the next class we will try to convert one primal problem into dual. Thank you. Stay safe.